Which one?
Yes, I need to project. I have one too. Okay. So I don't mind. Nobody else is. Okay. Okay. Well, you know. So I have them all currently open in PDF.
We'll give you the result, put in the proceeding. If we don't have access to the proceedings, I just have them for my work.
So I mean, basically, what I have is I have everything open in order here. So I don't have 5 minutes ago. I have an hour.
Yeah,
45 minutes ago.
good. Yeah.
So we can switch to your. Okay. Let's see what's this. Because I need to go to So where is hello. Hi, everybody. It's time to get started. This is the Lpwan BOF. So the blue sheets should be circulating out there. Should record yourself on them. We do have somebody who's willing to take notes already. Is there somebody who's willing to act as a Jabber scribe? We sort of need a Jabber scribe. I guess I can. Hello, do we have anybody who's willing to? Okay, just basically keep track of any comments that come in there and seek attention. So this is the Note Well, who you've all probably seen before, and you should know well. This is all subject to the IPR rules of the IETF and so forth. I'm Donald Eastlake with Huawei Technologies. I'm the BOF chair. Whenever you come up to speak at the microphone, mostly applies to people asking questions or whatever, be sure to identify yourself. It's best to do it each time because people who are remote can't see you, and you know, if they don't know, may not necessarily recognize your voice as being the same. This is the write-up that's was on the BOF page about the topic. Well, we'll be hearing lots about Lpwan and why it's needed. This is the current agenda. We're at the first item here, and we have basically a bunch of presentations on the problem. Why Lpwan is necessary, what kind of challenges there are in using IP with Lpwan. There is a gap analysis and some stuff on neighbor discovery. And the gap analysis and neighbor discovery, there's actually one presentation. If you're downloading these presentations from the meeting materials site, there's only one presentation for both the 15-minute gap analysis and the 5-minute neighbor discovery item. Then there's talk about AP level protocols, problems there. Then we have 2 talks on solutions, optimized 6-LoWPAN fragmentation header and CoAP kind of constrained signaling kinds of things. We currently allow a half hour for discussion, which should hopefully be adequate on our schedule. This is not a working group forming BOF. It's to get a feel for what's going on with the problem and what direction people might like to go. And a little bit at the end for wrapping up. Does anybody have any bashing they want to do in this agenda? Things they want to change around or add or delete or anything like that? Brian, is Brian Haberman here? Does he want to, alrighty, does he want to say anything? There you go. Okay, go ahead.
Brian Haberman, you're, I guess I'm your host for the next 37 seconds. Like Donald said, the main thing here I'm looking for is a couple of different pieces of input. One is just how much of a problem this is and how interested people are in working on the problem if it is a problem. So if you hear me jump up very quickly and say, hey room, what do you think of this? I'm expecting people to jump up and provide input. Thank you.
Okay, so I guess we have an agenda and we have, I think, some good speakers and presentations. So the next thing is why Lpwan? Okay.
So I will just switch over.
Okay, if you want. Sure. If you There may be some very minor changes in some of these presentations. All the slides presented will be updated right after the session, but they're only very minor changes. You have the slides online are very close to these in all cases.
So hello everyone, my name is Alexander Pello, and first of all I'd like to thank you for being here in this great room in this great city of Buenos Aires. Where we have come here for a very interesting thing. It is to start talking about a revolution in the making. So I will start with a very short 5-minute pitch on the business side, why this is really a very hot topic and why we are getting interested into this right now. There have been short minor changes in the agenda because we just met and said, okay, we don't want to repeat a couple of things, but you will see this as we are going. So Lpwans, why and what are they and why now? Well, for the past couple of 20 or 30 years, we've seen a lot of a great evolution in wireless technologies. And this evolution has been very often or almost exclusively into always going to very growth into user data, growth into throughput, which has been accompanied by growth into cost, energy, energy consumption, and requiring licenses and so forth. And for the past around 4 years, there have been a couple of companies that actually went there and said, okay, for the Internet of Things, we don't really need this huge throughput. So what they did was develop technologies that are actually very, very low throughput. And these technologies, they have some really amazing advantages. One of them is they cost really, their cost is really low. For example, covering a country like France with the infrastructure for a telecom operator is something like $5 million for the hardware. On the energy side, you can have devices that with one normal battery can function for 20 years. And also, they can function in license-free spectrum. That means that you can have a huge spectrum of applications that can profit from these applications. This has been also recognized by the 3GPP. So right now they're working on NB-IoT, and probably in 5G technologies, these types of communications will be included. So lots of applications for the smart city, connected street lighting. You can have water meters, you can have gas meters or whatnot. You can have your private networks. So really huge application potential. And if you look at the numbers, well, right now we're in around 2016. Well, very, very little number of devices, but by the year 2020 or 2023, it is expected to have 1 billion devices. This means that the work that we are going to be doing here today is going to get implemented and included into these 1 billion devices. This also means that all technology developers that are actually developing these LPWAN technologies are feeling huge pressure on them. They are seeing this huge market there and they're saying, okay, we really need to get the technology out. And they don't have really the time to think of all the things that we are asking, that we are trying to answer. So this is the thing why we are here. We are at the right moment in this kind of a revolution. So Anna will be talking a little bit more on all the good and bad characteristics and the specific things on these technologies. I'm going to be talking a little bit on the ugly part, as I said. Well, we have several competing technologies. Of course, that's normal. They're proprietary. They're not really networking oriented. And a lot of the times they are actually trying to build, they're not trying, but they're falling into building vertical silos. And there is no IP there, not even not mentioning. There is no way to interconnect them to the internet and whatnot. So what we're seeing here is that these things, these networks that are really beautiful, well, we have a huge variety of technologies, and people are saying, okay, we want to get these 1 billion devices in a couple of years' time, and we want this really, really fast. So this is what I would call the triangle of death, where all these variety is really actually doing a little bit of harm to these technologies. So the only number I'm going to put out there, and this is not pesos, but this is US dollars, so I don't know how they calculate this thing, but there are lots of billions of money out there to be taken by the year 2020. But the thing is that the radio technologies are there, and people are just saying, okay, we want to get as fast as possible there. And what we're saying here is we would really like to keep the momentum. Our goal is work with these technology providers, bring IP and the IETF stack to these LPWAN technologies, and help them really live up to the expectations that they're having. Thank you.
Okay. Go ahead. Yeah, if you have time for one question.
Srigandavelli Cisco. As just a minor comment on the $589 billion. Every time I see the market size for IoT, I see a new zero at the end. So I don't know what to believe, but I completely support this work. So
Thank you. So you changed the order?
Yeah.
Okay. All right. So we'd like to, actually, you should have been brought up during agenda bashing. We're swapping the order. So the gap analysis is next, followed by the IP challenges.
Hello, this is Anna. Then I will present the work we have done in the mailing list. Then I'm only editor of all the discussion and the feedback that we got in this mailing list. I want to thank everybody that participate in this mailing list, that give the ideas, the technologies, and all the stuff we are going to see next. Then the outline of my presentation is which are the LPWAN's technology we got, which are the characteristics, which are the probably the best things the IETF can bring to these technologies, and the challenge they bring to the protocols. And then I will make a review of the gap we have in the IETF protocols to give a solution to the LP1. Well, this is not readable, I know. You can look at the link to get the table. But what I want to show is the work we have done in the mailing list. This is one part of this work. Then we really give freedom to everybody to participate and put the technologies that they think could fit to this LP1 mailing list. Then here, I have 2 slides. Then as you can see, there are a lot of technologies that have similar characteristics, not the same, but similar. Then what we can get here is that we have range. I don't know if I can put this. No. Then we have range that are long-range technologies. They are using almost the same spectrum. They have asymmetric lines. They have a very low throughput, very slow data rate. What is different is that the encryption and the modulation are different. The algorithm is different. But nevertheless, they have a lot of common characteristics. Then here I present what I would like to do is to make an LP1 family, and I put all the names of these technologies here, and I say, well, the general characteristics, what are they? As defined in the RFC 7228, they are defined as constrained and challenge technologies. But what else they have? They are property industrial, they have potential. They are battery-powered devices with very limited communications. They have a small message size. They have also limited number of messages per device and per day. They have no IP capabilities. They have no, or they have a complex device and network management, or not at all. They have, some of them, a fragmentation at layer 2, or not at all. Another important thing, they are asymmetric lines. And more specifically, what we got there is that we have then very small packets, then between 15 and 100 bytes. We have a limited number of packets that we can send per day. Then I cannot have a flow. Then I have a very low bandwidth. Then these packets is sending very slowly. There are a lot of error. I have a lot of lost packets. I have a variable MTU. I think that the modulation will change per packet, perhaps, or per day. Then I can change this modulation. This means that my payload will change. I have thousands of nodes. I have sleepy nodes, but not as in DTN networks. This means as they only send in 10 packets per day, all the rest of the time they are asleep, okay? But the network is there. There is not at all, or sometimes fragmentation. And some of these devices are mobility, but not as mobile IP. I have no connection, I have no flow. And the most important part, one important thing, is that the topology is star topology. Okay, let's see what the IETF protocols can bring to these technologies. The first and the most important is the IP communication. This means I will have an end-to-end communication to manage, to control, to defined to all these devices. Also, we will get solution independence of layer 2. This means that if layer 2 is more complicated, is changing, or is another thing, I can get the same solution. I can adapt or use the actual protocols. We need to do that. And we can use also the existing addressing spaces and name schemes. And another thing that is very important is the security. Security is very important because of the application we are doing with these devices. The applications, most of these applications are personal information. For example, I can know at what time I get a shower today at 8 in the morning and it lasts 30 minutes. I don't think that anybody wants to share this information with the others. Scalability, because nowadays, as there are proper solutions, scalability is not concerned. We have also to get a high reliability and interoperability of these technologies. And of course, I think that the IETF protocols as header compression is included in the solution for LP1. Well, now I will start doing an overview of all the actual IETF protocols and more or less what is missing or what we are going to do, what is missing or what we need to do to adapt them. For example, well, I start with IPv6. Then IPv6 will include or will add a very big overhead to these LP1's technologies. It doesn't know how to manage a variable MTU, and there is no very good solution for fragmentation. We need to adapt also the neighbor discovery protocol, because I think that LP1's technologies cannot do learning. They need to have the information in order to communicate. We cannot do learning like we have to search if this is the correct address. We need to know our address in order to communicate. There is a draft who gives a very deep analysis of IPv6 problematic, draft Gomez, LP1. I will introduce it at the end of my presentation, more or less what is saying this draft. Okay. Next, I will go to the Lpwan and Syslow protocols. Then Lpwan, as you know, reduce the header overhead, and it's almost used, or it's traditionally used for constrained networks. But constrained networks in Lpwan is not the same as LP1's networks, because LP1s are more constrained than the Lpwan networks. Then I can categorize these LP1s as a challenge networks for the header compression solution. Then also, for example, for Syslow, we have some difference between Syslow and the LP1 constrained devices. Because LP1s are also constrained, but they are different. I mean, they are sending, for example, they are sleepy nodes that they don't have in Syslow. We don't have flows neither. Then the solution is different. Then we also have in this part of reduction of overhead, the ROG header compression that has been adopted by the NB-IoT, then the 3GPP NB-IoT solution for the LP1 devices. But again, ROG compression is a good protocol for multimedia flows. Then we don't have multimedia flows now. We have to adapt the solution of ROG, the good things that ROG has and the good things that Lpwan has, to produce something to solve this overhead in LP1s. I go to 6-ish, then 6-ish is similar, but they are different. Because 6-ish use the synchronization to determine to perform determinism. And 6-ish is a mesh infrastructure, and we have a star topology. And then LP1 doesn't do slot channel. For routing, as we have a star topology, then we are not doing routing. Perhaps in the future, some new topologies for LP1s could need a routing protocol, but not today. Core for LP1s, then we believe that the co-op solution is a good solution for LP1s. But we need to adapt this solution for the duty cycle and the limited throughput of the LP1 technologies. Mobility, then, as I said before, mobile IP is not adapted to the LP1s because we are not in real-time communications and there are not so many packets. Okay? Thank you. If there are questions? Yes.
Hi, Juan Carlos Zúñiga. Have some questions regarding the addressing, but I know the next part you're going to talk about that. So would you like me to refer my questions or?
Which one?
No, I'm saying that I have some questions regarding the addressing, but I think you're going to also talk about IPv6 addressing issues and gaps
Yes.
next. Would you like me to defer the
Of course,
question
yes, of course.
to that part?
This could be very interesting to complete the draft of Carles and the gap analysis. Yes?
Okay, so I'll defer my question to until
Yeah,
that part.
okay.
Manuel Bocelli, INRIA. I think this is a very interesting topic, and I think we need to address this in the IETF, and it would be really great to have IP protocols work on these types of devices and this type of radio technologies. There's one comment I would like to make is at some point in your slides you said that scalability is not a concern for us. I mean, at the IETF level. I'm not entirely sure about this because if you take this really one technology and you really have like billions of devices, even just adding like 1 bit over the air of IP related protocol data is going to make a huge difference. And so maybe it's scalability in a different sense, but it is a concern that we need to keep in mind. It's really important.
Eric Nordmark. So I looked up this earlier in terms of the range of characteristics that you have on this slide, and it seems like it's a fairly wide range. And I'm wondering whether we think that we're going to go after the whole range of characteristics that's here as opposed to focusing in on something, because looking at like picking an example, 10 packets a day doesn't sound like a lot, right? We try to avoid having chatty protocols, but getting things down, that low might be a lot of challenge. And maybe you want to have a different approach to dealing with those, as opposed to something that's a bit higher packet rate, whatever, right? But is the thinking currently that we can find one solution that spans this whole range and it's a single solution?
Well, I think I can say it as in Latin America we say it. No podemos prender dos velas al mismo tiempo porque ponemos el fuego. We cannot turn on 2 candles at the same time because we put fire at the home. Yes, of course. Or we cannot split. You cannot split yourself to things. Yeah.
Yeah.
We need to choose, I don't know, 2 or 3 technologies to focus. I think it's, yeah, I don't know which
Okay.
ones, but yes, we can discuss about this in the mailing list or personally
Okay.
to see which could be the best technologies we can take and study, deeply study to see, to get the solution. Yes, of course.
Yeah. That makes sense.
So we do have some time for discussion later. I'm going to cut off the line. You can ask questions, but just try to be fairly quick.
Okay. I'm Subir Das. Quick question. I was just trying to understand, is it the problem that running IP over this wireless network technologies is a problem? Because I think all the gaps were listed, but I don't see what is the problem of running end-to-end IPv6 over this, for example, 802.15.4. Is there any problem, or is?
We do have a separate presentation on IP challenges. So.
Okay, because there are devices
Yeah.
deployed today, millions of devices for running end-to-end IP.
May I take this question after personally? Okay.
So one question I have is like the lack of IP adoption by any of these SDOs, like LoRa or Sigfox. I don't know about Sigfox, but is it mainly the ND because the ND is not optimized? Is that the primary reason? Do we have any documentation from this SDO saying that we have considered IP, but we have decided not to use IP for these reasons? Did they state those reasons? No?
Just to correct you, if you want to run Samita Chakrabarti. So, so you just mentioned that the problem is optimized ND, but for 6LoWPAN type of devices, we have optimized ND for that, for those devices. But maybe there are different reasons they don't want to run IP because they don't traditionally run IP. They don't probably are not familiar with how IP world works. So that's one of the things I see.
Right. I think I know the 6LoWPAN and other things, but I was coming to that point as, did they even consider any of the existing protocols? Because, any of the specs, LoRa doesn't even talk about no mention of IP at all, right? That's the thing I'm trying to understand.
So Alexander Pelov, I just want to pitch on this question. So this was actually the reason why I wanted to start with. We have all these billions of devices, and everybody is just trying to get there as fast as possible. Everybody thinks we have the solution. Then everybody goes and deploys around 10 capture sensors. It works. 100 sensors. It works. 1,000 sensors. It doesn't work anymore. So right now, all the things that we see, all the announcements, and it seems that it works. But with talks that we have with many companies, we know that there are problems in the back end. And right now, people are saying, okay, so how do we solve this? And we know that IP solves a lot of their problems. So there is no IP for the moment because they think we know everything. And right now, they're actually going back and saying, okay, maybe we could have gone a little bit slower on this one.
May I also tell you that I'm only presenting the gap analysis, but there will be more presentation after me with some solutions and more detail about the Lpwan's problematic, okay?
Just one final comment is, the problem is the gap analysis, it's lack of IP adoption. I don't know if I should call that as a gap or, it's a matter of convincing that SDO saying that you should use IP.
Next.
So, we should.
Dan York, I had a similar question, I guess, which was that in the gap analysis that was there, what I guess I would love to, my feedback would be, what would be helpful would be to understand for each of those, if they're not using IP, what are they using? But I saw the packet sizes and things, but I didn't get a sense of what is the networking technology that they're using. Is it proprietary? Is it, what is it? And so, unless I missed it, but that would be one point would be, I'd suggest that as something to, go ahead.
Thank you very much for your question. Actually, it comes a little bit in my slides afterwards. It's you basically put your application data directly on your Mac layer. So you have your Mac frames, and then you put your application data there.
Oh,
so yeah.
So basically, they're all making up their own protocols, essentially. Okay. Well, the second question, I guess, which was in these devices that are here, do we have a sense in the gap analysis? Do you have a sense of whether these devices have enough capacity to support an IP stack?
Yeah.
Yes or okay? Okay. Anyway, those would be my, I guess, the questions. And
Yeah, once again, here actually in these networks, it is the network that is the most constrained part of the whole network. You can have a pretty resourceful devices that are communicating over extremely constrained network. So here we can allow to do a lot of compression stuff in the end node, and the only precious resource is the network. There are some limited devices in which we can do, we should maybe take care a little bit of what we are doing, but it is really the network that is the tightest spot.
Yes, I have a question from Jabber, from Basabara Patil. You mentioned Sigfox and LoRa which are already deployed and they do not need any help from IETF. So how do they benefit, for example, from this work?
Well, that's pretty much very similar to Sri's questions, right? I mean, why should we come with the IETF and propose solutions? Well, I think Alex has answered a bit of that, I mean, a lot of that actually, that they have an end-to-end solution for one particular prime and for one particular scale. And now they are facing, they have not stopped the work. I mean, LoRaWAN is meeting this week in Santa Clara to look at, for instance, the join process. So it's not like everything is solved. They are looking at version 2.0 already of the LoRaWAN. I mean, things are evolving. And part of the problems they will have to handle is the scalability of the system, the management of the system. That's basically, you're asking the question that we'll be discussing for the next hours in the next slides. So what I suggest is we go through those slides layer by layer. That's really how we organize this. And layer by layer, we ask the questions. But basically, in background, there is this question, right? Why should they ever go IP? And that's basically what we'll be trying to demonstrate during the next hour. Okay, so let's not just jump to conclusion.
Okay, I have the only thing, just for me now, there's a version of LoRa which is slotted, which you mentioned that none of these technologies were slotted. LoRa B is slotted, which is supposed to be. Okay.
Yeah, well, I mean, in the general, LoRa is slotted, but the other are not. Okay, we have both. Yeah.
So I cut off the line earlier. We really need to move on. We can ask questions during the discussion later if you want. Unless it's really quick.
Not very quick.
Okay, thank you. Yeah, we should go to the IP challenges.
Okay, so we've been through two presentations already. So Alex has shown us that there is a big market coming up with a huge momentum that has already formed. There is already a number of contenders, and Anna has shown us that it's not just 2 or 3, it's more like 15 or something. And then Anna has showed us that there is a number of features that the IETF could propose and to help solve the problems that are happening in that space. But at the same time, the solutions that the IETF has developed were not aimed at such constrained networks in particular. So even if we have something close to what's needed, we still do not have the exact solutions that would help those people develop their network faster and keeping the huge momentum that they have already formed. So what we are going to do next in the new next presentations is go layer by layer and show where the IETF could actually propose some help, propose some solution. And I hope that Juan Carlos comes up as well, because it's not only the IETF which is looking at this, but the IEEE is also looking at this for the lower layer. For instance, the address discussion that came on the mic for. So it's good to show that not only do we have this momentum in various standard bodies and all those siloed solutions, but there is also the IEEE and the IETF trying to help this happen, trying to get some more homogeneity into the solutions that are being deployed, in the way they are being managed, in the way the devices are being addressed, etc. So I'll be discussing mostly the lower layer, the IP and a bit of co-op UDP, and you will see why I'm doing this. And then after me, Alex will come and discuss the security and application layer. So, and you will see at each layer where the IETF could bring stuff that would help those protocols keeping their momentum and the velocity and the speed at which they want to go to market, still get something which can evolve and survive over time. So there was this question about the size of the stack and the size of the packets. As Alex said, the size of the stack can be important, but that's not necessarily the crucial part, because as you know, the size of the device, size of the silicon, the consumption of the silicon keeps improving. What doesn't change is channel. What doesn't change is the properties of propagation of the radio, how far you can get, how much data you can transport over which distance, using which energy. So all those radio technology are about trade-offs, and how you play with those parameters to get at a certain distance with a certain rate, within amount of energy that you can spare. So as Alex said, the most critical thing is addressing the size of the stack. And at the IETF, we've got 6LoWPAN in one hand, and there are good things, and we'll be discussing that in more details, but there are good things in 6LoWPAN, good thinking that we can reuse, but 6LoWPAN won't give us, Emmanuel mentioned that, I mean, the number of bits in the air is really critical. 6LoWPAN could optimally go down to 4 bytes to transport UDP, up to UDP. That's not enough. We need to do better. ROC can do up to 1 byte, but ROC learns the flows on the fly, and that was mentioned already. There is no way we can learn things on the fly. Those devices need to know everything they need to know from day one. The states that needs to be installed in the network and the device must be installed at the beginning before the flows need them. So the dynamics that you see in ROC are not adapted to the IP network, to playing IP in this world. What we really want to achieve is go down to something like 1 or 2 bytes up to co-op. So the question was asked about the size, and clearly adding IP and DTLS will increase the size, and maybe NS has a point on that. But ultimately, as long as the code you place in there is not used just once in the life of the device, if your security stack can be used not only for joining, but also for protecting data later, then it's worth the investment.
Just a small remark. Of course, if you not include, for example, DTLS into your calculation in a comparison, of course, then the version that doesn't have it is obviously much less lightweight, but of course it doesn't provide the same security benefits, which I think, and the question and ultimately boils down to what specifically are the security requirements. And I think that's where people tend to say it's like heavy, Bluetooth Low Energy is also heavy, 80 kilobytes, but it just provides security at a different layer. Just there's no free lunch with security. If you leave it out, then of course it will be more lightweight, but you will have other issues.
I can only say yes and yes, and add that those devices will stay deployed and managed for 10 to 20 years, meaning that whatever security properties, whatever keys, whatever management you've placed in those devices will have that will be the only thing you get to play with to protect this device for 10 to 20 years. So you better think seriously about how you put your security in those devices and which kind of tools you enable on those devices. So then again, there is a lot of experience at the IETF. There are all the good people who know pretty much everything about this. So the experience from the IETF could be useful to design devices which can actually stand the experience of time. And now, okay, the question was asked, do we want IP? Do we have IP? And Sri asked the question at some point. There are some networks which don't have IP. There are some networks where the people will never want IP, at least on the wireless. And probably the IETF should consider addressing that case where the last hop is actually not IP. It's not just networks like LoRa. For instance, industrial network like wireless HART are designed just the way Zigbee was designed, with a MAC layer and the application just over it. No layer 3, no layer 4. It doesn't mean that you can't do anything. It means that maybe we can think about inserting layer 3 and layer 4 at the gateway, at the first hop. And the model for this is what we call the remote I/O. The remote I/O is really considering that your gateway, what they call the gateway in that space, is like a PC with a serial cable, and that the sensor, the device, is attached to this serial cable. And when you want to talk IP to this device, what you really do is talk to the IP address of the PC, which terminates the IP and transport, and now does its thing over the serial. This model has existed forever for talking to serial devices. This model could be extended, and there would be huge applications for that model. Maybe not in LoRa. I'm not saying that LoRa wants that, but for instance, I listed wireless HART. Yes, I did. So there are a number of protocols which now have this desire to go IP to the device, but the protocol on the air itself does not support it. And so there are efforts to emulate IP, go IP as far as you can to the last hop before the device. So that's one thing that the IETF could be looking at, is how could we basically serve that remote I/O model. Now, for those that we could consider moving to IP, as considering that if this group is formed and it's successful, then we effectively would be providing a new way of compressing IP that would fit the needs, like 1 or 2 octets to compress IP and UDP, and co-op maybe. Then what are the benefits for the cost? And well, we'll be discussing that for the next hour, but the benefits are huge in managing the device, securing the device, and a lot of that, as we observe it, is actually happening over co-op. So it really looks that in that space, IP is a commodity to address the device, but the critical hourglass is probably not just IP, but co-op. Because co-op will give us a way to authenticate the device. There's all this work happening, like COSI, where you do all the authentication of a co-op. And we've got all the compression, we've got CBOR to actually shrink the data that we are passing. And co-op also has the URI, and you know that in some of those LP1 models, it's only one application. There is no way to actually dispatch what's being sent to maybe a management application, maybe a application A and maybe application B. It's just meant for a very simple, this device is done for this application and the application server is this, and the identity is managed by the application server, by the way. Well, if you want to actually be able to dispatch, and we found everywhere in life that we always wanted to dispatch at some point, then the URI in co-op can be the critical thing that we can use to dispatch. So there is value if you think about survivability, if you think about building something now on which we can build for the next 5, 10, 20 years. You need to think about those things, and that's typically where co-op can be a critical service. And then, I mean, we said it, we'll re-say it. If we can't compress IP UDP co-op down to 1, 2, 3 octets, then we'll never be able to convince the most stringent use cases. So we know we don't have a 6-LoWPAN solution that fits the bill. We know that ROC does not fit the bill either. I mean, NB-IoT is considering ROC because that's the best they have, and they have it included already in their stacks. But because of the dynamics aspects of ROC, at many times you get to send most of the frames, and even sometimes, well, more than the frame size because you have a ROC header. Right? And we can't afford that. We want to know what we send from the first frame to the last frame. So what we're really after is the best of both worlds, having context like 6-LoWPAN so that we know what we compress based on a context ID. And at the same time, we've got all the benefits of ROC, so we can say, oh, this is forever constant, this is variable. There is how you compute this predictable variation, or maybe it's unpredictable, so that you have to pass it in the clear. So having this data model that expresses exactly what is sent over the air, being able to put all the state in the device and in the gateway so that both are capable to virtually recreate the total IP frame. Well, that's the goal. That's what we need to do. That's what we need to prove to those guys. And if we get that, then all the opposition against going IP will go away. Question?
Christian Wittmer, Microsoft. I'm listening to what you're saying, okay? And I'm puzzled with that idea of why do they want to have IP there? And in fact, the big argument for having IP is not so much that we get better routing at layer 3, of course. It's because you want to move to an end-to-end model effectively.
You want to?
An end-to-end model. It's basically all the solutions are not IP, rely on some level of intelligence in the gateway.
Mm-hmm.
And the more you have intelligence in the gateway, the more you're in a situation where you can only develop something new in the endpoint if you also modify the gateway.
Yes, the end-to-end.
So basically, what you seem to be looking for is a way to be able to update the endpoint without changing the gateway. Because if you have to change the gateway at all, even just a little bit, for each thing you do, then why not have the intelligence in the gateway in the first place? I think that that's kind of the design that you want there, that you want to eliminate or limit or specify the complexity of the gateway, but basically the application can evolve much faster than if you had to change all these things.
Yes, that's good summary of the end-to-end principle, knowing that we probably include IP, UDP, and CoAP in the hourglass when initially we would only have IP. So IP here is mostly...
You definitely want to have IP.
You do.
You may or may not want to have CoAP per se.
But
you definitely want to have IP, yes, clearly.
But you realize probably, I mean, that's a guess, right? That the IP endpoints for a given device will always be the same. So they may differ from one IP device to the other, but this device may probably all its life talk to the same IP address on the other side. And then that's not the gate. Well, we have to
they may, but you don't know which one, and you want to be able to change that.
We want to be able to address multiple applications and multiple services. Does it mean that the IP layer takes you all the way? I'm not sure. Usually we want to do what you say. It's not very clear that in that particular space they want to do this.
Well,
now, we don't want to go and change the gateway near the device, but there is something that talks to the device somewhere in the network. And
well, it's very clear that when you do end-to-end, you want to be able to deploy new software on those two ends, or maybe change one of the ends. You want to be able to do that without changing the infrastructure.
Yes, that's true.
Because,
yes,
and that's kind of the fundamental thing that you want to do there. And
right.
Then everything follows from there.
Right. That's true. I mean, that's the question about this.
And it's, I think, Pascal, you described it quite well to what Christian was talking about in the sense, I actually see it in a similar way when you talked about this remote I/O. I think that's a very interesting way of phrasing it, because for some of the technologies, specifically the short-range radios, I see them more as a cable replacement. And a cable replacement. Yeah, like exactly. You would normally attach a mouse to your computer without actually having IP addresses at the mouse. And there were even products that did that for whatever reason. You can also see these wide area networks in the same way. And you said, like, how do I actually identify for an incoming packet, how do I relay the message without actually having all the overhead of the payload overhead of IPv6? But of course, also in the other direction, how do you avoid having all the overhead with identifying the server, the application server you want the IoT device to talk to? And there's certainly expectations, deployment expectations from the different companies who develop various different radio technologies on how that's actually going to work, which ties a little bit into the earlier mentioned security mechanisms as well, because it seems to me that some of the companies are expecting that the operator would provide those services. At least it would be involved in deploying those services, because there's essentially it's like a nailed up connection, if you will, from the IoT device to whatever application service. And that also justifies the security mechanisms that is really provided at the link layer rather than at the application layer or something else. So I think one has to take those deployment aspects into account. But I think the way you phrased it in your presentation, I think is excellent.
And I need to add, Anas, that some of those protocols are already there. And for instance, I mentioned wireless HART because wireless HART is there to stay and the way it is. And now people want to address those devices as if they were IP devices, but they won't change the protocol to get there. I mean, that's lost cause.
Yeah. So for me, personally, it's not so much the question of like, how do we do 6-low-band and some other things. Maybe there are better ways to do sort of this multiplexing and demultiplexing. But I think where the value add comes in that we can provide is to, as you have shown also on the slide, we can provide some of these functionality like the device management. You mentioned the co-op work that was done in the OMA with firmware updates and fault diagnosis, et cetera, and because that's something these guys will have to come up with as well sooner or later, and we already have all that work highly optimized, CBOI encoding, co-op with shrink down headers and so on and so on. And I think there's real value in figuring out on how it works on those devices and whether there needs to be something extended in there.
Exactly.
So we're now about 5 minutes behind schedule.
Okay, I'm mostly done. I think I'm done actually when I say, yes, I mean, only one slide. Anna mentioned there are so many SDOs. Eric came in and said, well, I won't paraphrase what Eric said, but really there was this risk of boiling the ocean or chasing too many rabbits or whatever you call this. As Hannah said, we'll have to focus on a very precious few of those use cases which have enough in common so what we do makes sense. And then like 6LoWPAN did, starting with 15.4 and then evolving to other media, then with 6Low. Now we can always decide to continue the work for other standard bodies, but we need to elect 1, 2, 3 of them. We need to actually discuss on the mailing list before we go, hopefully in Berlin for workgroup forming BOF. We need to have elected those standard bodies. We need to have talked to those people and see if there is a cross interest. If they are interested in working with us, if we are interested in working with them, if we can do cross-participation, we have an excellent example of that between 6TiSCH and 802.15.4. This is just marvelous. If we could have something similar with the Sigfox or the LoRa or the NB-IoTs of the world, then I know we can make that work because we've done it once.
Juan Carlos Zúñiga. So I'm taking now the opportunity. I know we're behind on the schedule, but before we move on to higher layers.
Yes, we go. So you do now.
Yeah. So first of all, excellent work. I think it's amazing what you guys have done in such a short amount of time, and definitely there's more work to do. So great, kudos there. On the topics that we just discussed and Christian and other people's points, I agree. I think we have to make a thorough analysis of what exactly are the needs of each one of the layers, the services, and do we actually need them? Like Anna made a good point of most of these technologies have star topologies, right? So by definition, there's a central point of communication to the rest of the network. Do we actually need end-to-end communication in those networks and so on? So those questions I think are critical here. Also, the other point I wanted to make is, as you mentioned, in the collaboration with IEEE 802, right now there is the work in the PAR 802C, that is looking at the local addressing for the MAC addresses, and this is the evolution in IEEE from OUI to EUI to CIDs. I don't know if you're aware of both, but basically assigning company IDs and trying to make use of the local space. So right now, IEEE 802 is looking at how to better use that addressing range or that addressing world. And it's a perfect timing to consider this type of use cases. Over there right now, they are considering different use cases, but I think that the timing is great to not having to fix something later on one side, having after starting the work here, we can both progress the work together in both organizations, I think.
Okay, we need to move on to the next.
That's fantastic, Juan Carlos. What I realize with your words is that first, the IEEE is seeing the same thing as we are seeing, that we need to help them do the right thing so they can really thrive. And the second thing I'm seeing is probably we also need to work together as a triangle, because there will be this interaction between the layer 2 and the layer 3. And for instance, your 802C MAC technologies that maybe will impact the way we do our compression, I don't know. So yes. I mean, so whatever we see here at the IETF, the IEEE is also seeing it, and they're also addressing it, and that's great news.
Thank you very much, Pascal. So it will be a bit difficult to take the word after you, because you so eloquently put the necessity of having IP at this device. So I will try to very briefly introduce what are the challenges that we can see on the upper layers on which we here at the IETF have already running solutions where we can contribute, maybe with a little bit of slight modifications or BCPs, but we really have a lot of answers to problems that are pressing today for operators, technology developers, and that really make them redefine some things right now. So I'll start with a couple of slides that have been provided by Rafa Lopez and Dan Carrillo, if it's pronounced like this, which are on AAA. So when authorization, authentication, and accounting. So this is actually a very huge problem to operators that are trying to deploy their networks. For the moment, you have the deployment of the networks, you have the billions of devices coming, and you have 1,000 devices there, or 5,000, or maybe 1 million. And so the first people that are actually right now coming to the 1 million, they are seeing the problems. And the thing is that before a device starts communicating with the network, well, you first actually need to authenticate the device. Then you need to, of course, allow it into the networks, which is the network access control. And in general, what's happening today is everybody's just using pre-shared keys. Everybody's saying, okay, you know, we put in the pre-shared keys and we know how it should work. At Lpwan level, we have some specific requirements. How do we manage the how do we manage the AAA process when we have a huge number of devices? We have severe constraints in bandwidth, throughput, duty cycling, and also we have a different time scale compared to what classical protocols have seen until now. So we really need to get this low level. So we get into the network in a much slower way. What can the IETF offer into this area? Well, we already have protocols that have been used and that are used by operators to operate networks with millions of devices, let's say, radius and diameter. We have some guidances that are already out there that help people manage their keys and so forth. We have frameworks, we have the extensible accounting protocol, and most importantly, well, they are independent of the technology. So you can use it for a LoRaWAN or for a Sigfox. I don't know on a Sigfox how it will be working, but you can use it on different types of technology. So this is what we can offer right now. So what LP1s actually have right now in this very moment as a problem, as problems, and what they're trying to solve is, can we live with pre-shared keys when we know that there are going to be end devices that will be there for 20 years, and you know, people can just go there and maybe can look at your key. How will this scale? How will this be flexible? What should an AEEE, what should be the good AAA model for this? And for example, LoRaWAN, they have a joint process in which end device joins a network, so which is basically authentication process. And right now, in this very moment, maybe a couple of hundreds of thousands of kilometers away from here, they're actually trying to redefine it because they have problems. We here at the IETF, we have the toolbox to offer them. We have EEP, we have work going at Anima, at the Anima working group, starting right now at 60 solutions. we can adapt radius and diameter in a with very simple modifications to what is already existing there. And this is a thing that we can provide today. So this is on the AAA right now going into the management. So when you want to manage a device, an end device like this, what do? As I said a couple of minutes ago on the mic, today's LP1s, they're basically, you have only the MAC layer. And when you want to manage something, well, what you are using, MAC commands. You're saying you're forging some special MAC frames, and you send to the end device, and you say, okay, right now I want you to configure, I want to do this, I want you to do that. Well, this thing, it's not very flexible. For example, in a LoRaWAN, in a LoRa network, you have 3 parameters that are orthogonal. You can specify each one of them independently of the other, spreading factor, coding rate, and bandwidth. So you have 60 different possibilities. Right now, in the MAC specification, there are 16 possibilities. So if 5 years down the road, someone decides, oh, okay, this combination is really very performant, and I really like it. Well, it's not possible to configure it. It's not that. You need to change your MAC layer. So it is really important to keep compatibility with what is already out there. The MAC specification should be left as simple as possible, but we must provide some way to actually do some scalable, flexible way of doing things. Something that is not dependent on the layer 2 technology, and something that actually enables you to manage a huge park of end devices. Also, how do you do application management on your devices? Well, for the moment, a couple of slides later, I will show you, but for the moment, application developers and device developers, they're actually left to their own resourcefulness. And basically what they do is, well, they put out a device, everybody gets excited because it's a LoRa device or it's a Sigfox device, everybody buys it. And then people say, okay, how do I change a parameter on this thing? Well, surprise, you can't. And here we have the protocols that do it. We have one example I can give it, but it's not the only one, is we have COOL or COMI or lightweight M2M over CoAP. And you can actually use this to configure also your application by keeping your protocol stack very lightweight. And this helps the application developers. So what can the IETF offer today for managing these devices? Well, managing large-scale deployments. If you want to have your small-scale deployment of 100 nodes or whatnot, well, you already have LoRaWAN or your other, this is the example I'm giving also with LoRa. Excuse me, this example, the case is the same across every one of them. So if you want to really scale, if you want to live up to the momentum that is expected of these technologies, you need some more complex solutions. You need things that require more, that provide you with more flexibility, things that integrate with your existing infrastructure, that are compatible with your network management service of today. So this is things that we can do. We are adding this layer onto the MAC managements that exist today. On the security part, well, LPWANs have a particular set of problems. Well, first of all, you have a couple of technologies that are very asymmetric. The Sigfox network, you have 140 messages per day on the uplink, 4 messages a day on the downlink. Maybe this is some kind of an extreme case, but you have the whole spectrum. You can have communications that are symmetric also, and so forth. So here, this is a particular constraint. You have low throughput networks that are maybe in some extreme case 50 bits per second, and you have some duty cycling. And this actually allows for rethinking a lot of the things that have been unthinkable in normal networks. For example, for a Sigfox network, if you want to have a one-time password, so basically you want to XOR and you have your perfect security, to secure a device that will be existing there for 20 years, you only need 20 megabytes of one-time password. 20 megabytes, it's, I don't know how much it costs, but if it's an SD card, it costs maybe 10 cents or something like this. So you cannot reasonably secure like a 3GPP device for this, but you can reasonably secure a LoRa device like this or a Sigfox device like this. So things that have really in classical security aspects are not reasonable, here are really reasonable. So we can really rethink a lot of our assumptions. So what we can propose here, use COSI for asymmetric security. We have the right people to think on security issues. So this is what I'm going to say about this. And AAA management security applications. LPWAN applications are different. Typically, you have a limited number of data flows. Data flow for the control traffic, maybe one application running on your end device, two applications. So you can really, with using some context, compress really well your networking protocol, your networking stack. The traffic type is a little bit different. So as I said, so quite asymmetric. And of course, applications run on different time scale. And devices will exist years and years, maybe 10 years, and they will send messages at a low message rate. On the other side, business applications that communicate with these devices, they will change much more frequently, and they will have, they will provoke a lot of traffic. So the applications run on a different time scale, and here, when we were talking about the end-to-end model, it is really important that the network does not require every time to that you do not require every time to redevelop a new gateway when you want to deploy a new application solution, and you also want it to be able to run for years and years on. So just to give you an example, what's happening today? Well, typically you have layer 1, which is some kind of nice, very nice modulation that goes very far or very low under the surface. You have L2, a layer 2, some kind of a MAC framing, and then you have an application dispatch. In this application dispatch, you have your data directly. So this works pretty well when you have small deployments. But then it is up to application developer to decide when to want to ask for acknowledgements and when not. It is up to the application developer to decide how to manage the timers. It is up to the application developer and to the end device developer to guarantee that the data format is well known, how to manage sleepy devices, the downlink requirements, and even some of the layer 2, some of the technologies don't have fragmentation. So the thing here to really notice, there is an implicit application protocol. There is an implicit application protocol, and operators actually delegate this to the device manufacturers, and nobody is really sure what's happening there. And I see that, I think that you see where we can really help this whole ecosystem thrive. Really explicitly specify how to make this work in a really, really efficient and future-proof way.
One clarifying question, what do you mean by, say, like, the application needs to manage the downlink? So I thought if I look at least the LoRa architecture, it is up to the network server which is doing the downlink scheduling. So application is not involved in that. It's just passes the data back to the network server. So I'm trying to understand how much is all of these are application business versus the network server business.
So let's say that I'm not sure if I really got the essence of the question, but let me try to answer part of it. So network server, this is a LoRaWAN terminology. It's not really in all technologies that is there. One of the things is that your application must in some way ensure the downlink channel. So at some point you must wake up, you must send some information, then you must wait for some downlink information. And so here you need to have a very tight coupling between your end device and your business application. And this depends on the protocol?
Yeah, I think we have to look at the whole system. I don't believe, I think that view is correct. I think if you look at from application point of view, all of these, access architectures, you take Sigfox, LoRa, doesn't matter. You're fundamentally enabling a device to connect to the application. At that layer, they're just exchanging some payload. They don't know the transport, right? In fact, even from our point of view, we want that to be along those lines. Now, with respect to how you schedule the data, how you reserve the channel, these are all low-level business. That is, there has to be some network layer, some access point. Today, if I look at the wireless LAN controller architecture, the AP does that, or wireless LAN controller does that. If I map the same thing to LPWAN, NS does that, right? So I do not know if this is an application consideration. It is one layer down.
Okay, let's. I think that the acoustic here is not really the perfect one. You have, of course, you have the problem of the scheduler. The scheduler solves some part of the problems. It is when to schedule the downlink and so forth. Then again, it is when will your application wait for some information? How will your application know that, okay, at this point, I will need to receive some information. At this point, I will need to send some information and so forth. This is on the application layer.
That is the application protocol.
Yeah.
If I'm talking to, if I, as an application server, talking to a temperature server, I understand that protocol, when to query, when to expect the data. That is completely vertical, application by application, it completely changes. I do not know that. It's up to the sensor maker, it's up to the application talking to that sensor.
Can I answer to that? This is Alex Petrescu, also Alex, but Petrescu. So the problem LoRa have here is that they have an application that is specific to that link. They have an application that does the acknowledgements, the timers, the longevity, the CP knows the downlink. So everything is done in the application. If you take this LoRa application and put it on my PC at home, it will not work because it doesn't have LoRa or Sigfox. So this is why I think IP is needed here to have a IP protocol in blue down there with transport and app protocol like HTTP, for example. And then LoRa to write their own application if they want, but that could be run on a server in a server farm. And yeah, is this answering, Sri?
Thank you. So here the point is, okay, we have all these parameters and they are left to end device developers. And they're actually, it's not their specialty. They want just to get their device out there. And this is causing problems when you scale things. When you have 10 devices, it works. When you have a demo to make it works. When you scale up, it doesn't work anymore. So what is the value proposal? What does the IETF bring to the table? Well, of course, we have all these nice protocols that are out there. We have IP, we have UDP, we have CoAP over there, some other protocols. And here we really have the knowledge of what is important in these protocols, what should be preserved, how should we preserve this in the context, when we preserve context, when we do compression and so forth. And we can know how to play with some interlayer dependencies when we know, okay, here this will work in this way and this way. For example, one of the examples is acknowledgements, right? If we have acknowledgements on the CoAP level, maybe we don't need to acknowledge them on the layer 2. Timers. One of the things to address is timers that are related to this protocol machinery, and one of the big issues with operated networks is that the backhaul is actually changing the technology on which it is connected. You go from ADSL to satellite link, and then all your timers go really, really wacky, and your applications start to behave really badly. And this is a thing that we know and we can do here. And as I said, COPE compression and so forth. The second point is actually there are really open questions at the different providers of LPWAN technology, at the different operators of LPWAN technology related to all these issues. And So what we can do is we can help build sustainable technology. We can protect the existing system, help keep the momentum, and avoid solution divergence. The goal to say here is we have most of the things that we need, some best current practices, some minor adaptations, some very little standard track work, but I believe that we have what we need here in order to help keep the momentum and get out those billion devices working and keep everyone happy. Thank you.
Okay, that concludes the presentations on the problem. We have two presentations sort of aimed more at solutions. First is optimized 6-LoWPAN fragmentation header for LPWAN, and that's intended to be a remote presentation, which I haven't done before. So if the Meet Echo people know what to do, I guess Carlos Gomez has shown up in the corner. I can run the slides here, or you can. Okay. So slide 1 is currently being projected, so you can go ahead.
Okay. Hello, Buenos Aires. Good evening. So my name is Carlos Gomez. I am from UPC and I2CAD. I'm one of the authors of the draft entitled Optimized 6-LoWPAN Fragmentation Header for LP1. My co-authors are Josep Paradis, also from UPC and I2CAD, and John Crowcroft from the University of Cambridge. Next, please.
I can't hear too well. Do you want me to go to the next?
Yeah, thank you. Okay, so first of all, let's go through the motivation for this draft. So the 6-LoWPAN working group at the time had the main purpose of providing the mechanisms to support IPv6 over IEEE 802.15.4. One of the mechanisms designed by the 6-LoWPAN working group was a mechanism for fragmentation, which is included in RFC 4944, where the purpose is to support the IPv6 MTU requirement of 180 bytes, so that the layers below IPv6 have, this, well, for the layers below, packets of that size are required. However, 802.15.4 has a maximum frame size of 127 bytes. So fragmentation mechanism was designed at the time, and it uses a 4-byte header for the first fragment and a 5-byte header for subsequent fragments. So now, today we are considering to support IPv6 over LP1 technologies. We have already seen in the previous presentations that many of these technologies lack layer 2 fragmentation support. So in addition, the problem is that these technologies are more challenging than, for instance, 15.4, because some of these LP1 technologies have a maximum payload size which is roughly 1 order of magnitude below the one in 15.4. The bit rate in some of these technologies can be several orders of magnitude below the one in 15.4, and furthermore, sometimes there are message rate limitations due to regulatory constraints on the duty cycle. Next, please. So if we use or try to use the RFC 4944 fragmentation header, these may represent a very high overhead for LP1. And furthermore, the RFC 4944 specification defines an offset field which is expressed in increments of 8 octets. this has a consequence, which is that it only supports layer 2 payload sizes greater than 13 bytes. Whereas we have examples of very relevant LP1 technologies with a shorter maximum payload size than that. Next, please. Okay, so to overcome the described issues, we are proposing a new format for fragmentation, which we are currently calling 6-low-pan fragmentation header for LP1s, in short 6-low FHL. And as you can see on the slide, we have the format, which is a 3-byte format. There is, for the first fragment, first of all, a 5-bit dispatch type field, which indicates that this is a first fragment. Then there's an 11-bit field, which is the datagram size, which indicates the size of the original IPv6 datagram. And the last field is the datagram tag, which is a 1-byte field, which identifies the original IPv6 datagram being fragmented. Then for subsequent fragments, we have a similar structure, again, with 5-bit dispatch type sequence, which indicates that this is not the first fragment. Then the second field is a datagram offset of 11 bits of size, which indicates which is the location of this specific fragment in the original datagram. And finally, there's also a datagram tag. Next slide, please. So, okay, which are the main changes comparing this new format with that of RFC 4944? Well, first of all, the datagram size field in the new format is only included in the first fragment. So in the 6-low-pan fragmentation, the original mechanism, datagram size was included in all the fragments. That was done to ease the task of reassembly at the receiver, and also because since 15.4 networks can follow the mesh topology, reordering is somewhat likely. However, what we have in LP1 technologies is mostly star topology networks, so reordering is less likely. But nevertheless, the new format still supports reordering at the expense of some additional complexity of the implementation. Then another field is the datagram tag field. Originally, this had a size of 2 bytes. However, this has been reduced to a size of only 1 byte. This is because given the low message rate in LP1 technologies, ambiguities due to wrapping of this field are not expected. And finally, the datagram offset has been increased from an 8-bit field in the original specification in 6-low-pan to an 11-bit field, which now allows to express the offset in 1-byte increments. Next, please. So, which are the benefits of this new format, 6-low FHL? It is a simple, byte-exact, and short 3-byte format, which supports maximum layer 2 payloads of, even in the most extreme case, only 4 bytes. And it provides significant improvements in terms of overhead decrease. In terms of overhead, we can consider 2 components. The first one might be overhead in terms of the number of layer 2 data units which are required to carry complete IPv6 datagram. So in this table shown on the slide, we can see a comparison of the number of layer 2 data units required to transport an IPv6 datagram of several sizes, and also considering different possible layer 2 payload sizes. So as you can see, the new format reduces the overhead in terms of layer 2 data units, and the improvement increases with the IPv6 datagram size, and also it increases also as the layer 2 payload increases. Next, please. So on the other hand, we can also evaluate which is the overhead in terms of the number of fragmentation header bytes of the adaptation layer. And again, we have a similar comparison in this second table. And as you can see, there is significant overhead reduction by using the 6LoFHL, the new fragmentation format proposed in this draft, which again has some benefits which increase as the datagram size increases and as the layer 2 payload size decreases. Next, please. So we should take into account several considerations. For instance, this new format allocates 16 dispatch type values. So the first 8 values correspond to encoding a first fragment, and the last 8 values correspond to encoding the subsequent fragments. On the other hand, currently in the draft, the security considerations is empty. However, we are planning to provide content into this section in future versions of the draft. Next, please. Yeah, so that's the end of my presentation. I don't know if there may be any questions.
If not, maybe we can go ahead to the next presentation, and people can ask questions when the general discussion time comes up.
Okay.
You want to do your machine or my machine? Yeah.
No, this one you can.
Okay.
You can run it from
Or we can,
Yeah.
whatever. Want me to put it in?
Okay, so I'm going to present shortly a work that on which we've been working for 3 years now, and that's operating right now. There is a network, a LoRa network running on this. So this is the use of CoAP as a main control signaling protocol for LPWANs. So the goal is, of course, use CoAP as control protocol for LPWANs and to manage the full behavior of end devices, the end devices and the applications that run on them. The goal is to do this in a scalable, extensible, and efficient way that is compatible with current networking management services. And one of the things is that we can actually use CoAP before allocating an IP address, which is, for example, as it has been done by the copy draft, or through using EAP over a control port. So you can run your entire network with CoAP. How does it work? Well, first I'm going to make a little analogy with the LoRaWAN architecture. So this is a thing that's why I do this, because it has been seen by some people already. So just to make an introduction for you guys. So the end device here sends a radio signal, which is received by all antennas, all radio antennas that are close to this end device. And then the information is sent over to some server that is called network server in LoRa technology, in LoRa terminology. And here this radio antenna is called gateway. And then the network server interacts with the network controller to take some decisions, and the data, the application data is actually passed to an application server, and this application server typically exposes this to a business application over some kind of a API. And here you see actually where the end-to-end model is broken. So what we focus is, of course, bringing back the end-to-end model and the interconnection model. So we use a slightly different terminology because we are not LoRa dependent, we are technology agnostic. So the end node is called node F because it's a far away node, it's a far reachable node. The antenna here for us is simply a relay. There is nothing really fundamentally complex in it, so we call it a node R, radio node. And the thing that actually gets and processes all the packets here is the gateway, the node G. And we have a simple AAA server, so all things that come through this end device actually then directly go to some IP network, and you can, interact with the internet if you want. So how does it work? Yeah, so a couple of, so this is the terminology, and through the whole, I'm showing a couple of sequence diagrams, and so I'm only showing the node F that is, of course, interacting by using co-op with the node G. So the node F is the end device, and the node G is the gateway that makes the interconnection with the internet. And here we have the Lpwan constraints. You don't see the node R because the node R is invisible to the communication. It's a transceiver over there. So when a device boots up or something like this, well, it can go through all these states. First, initially it's disconnected, then it discovers the network. You can either do it reactively by just waiting for a beacon signal. So here you see that, so the node F and the node G sends co-op messages, and it is a post message to a well-known resource /G. We want the resource names to be short in order to not waste radio resources. Or it can be proactive. So you have the node that sends a GET request and receives a response. And in the response, in the content, the gateway provides all the necessary information for the node to join the network. So currently, LoRaWAN is actually trying to specify this. So you see, we are using standard approach, and without any effort, we managed to do this a couple of years before the layer 2 technology solved this issue. So this is a thing in which we can contribute to them. Once the network is discovered, well, the node joins the network. The node sends a post request, and in this post request specifies in the payload with a CBOR payload, specifies its parameters. And it receives a response with a location path which indicates the URI at which is located the information which pertains to this node. So after the node is associated, of course, if it is successful, it goes to the authentication phase. In the authentication phase, well, we just simply use EAP. EAP, we don't reinvent the wheel. There is a draft that specifies how EAP runs over co-op. It is this draft here, and you have a couple of exchanges. The default way that is already working is with pre-shared key. You can use a SIM card with EAP AKA, which is very, very efficient. You can use certificates, which is one of the demands that has been made to us by a company that said, okay, we really like the LoRa thing, but we have in our security policy a thing that says all the devices in our network must be authenticated with certificates. We ask people, how can we do this in LoRa? And they say, well, it's impossible. For us, it's a no-brainer. We say, okay, well, listen, it's LoRa. It's very slow. Your device will take like 1 day to authenticate. And they say, well, we don't care. The device will be there for 10 years. We can wait for 1 day for it to authenticate. So here it works. Once it's authenticated, well, you have all the application data that runs, and here where you can use co-op as we are doing, or you can use some other application level protocol. But for the management, we are using Cool. Maybe you are familiar a little bit with this work. It is been done at the core working group right now. If you want, you can use lightweight M2M. So this is another solution. So just to give you an idea here, it's the gateway that sends commands basically here to the device and changes its parameters. And here, well, the payload is extremely optimized. So here you can change 2 parameters in one go in an atomic operation, and it will take 5 bytes. Finally, you can switch to a semi-associated state. And this is a state which is typically for Sigfox type of network, where your downlink is extremely limited. And we have examples of how it works. Here, the key, of course, to ensuring the security is using object security. So using something like COSI. So this is a thing we are working on right now. And to disconnect, of course, well, you do a delete, you free the resources, and so forth. So not a rocket science. We are just basically taking what already exists and applying it to the network. On the layer 2, we can use LoRaWAN. For the moment, we are using 802.15.4 standard IEEE frame format. To give you just an example, so how would you configure the behavior of your entire node? Well, you go and you define a young model. It's done maybe in half a day or something like this. So this is a very basic MAC layer specification of a very basic LoRa device. And then you can configure all these parameters in the way you want. Maybe you can do them in one go, you can do them in an atomic operation, you can do it in a transactional way over many thousands of end devices. So here you have the young module that has already been published. And in order to configure all these parameters in one go, it takes 19 bytes with cool, which is working perfectly well for LoRa, even with the spreading factor that is the slowest and that will take most time. So why COSOL? Well, it is technology independent, can run on top of any frame, any Mac layer, can run on top of LoRaWAN, can run on top of Sigfox. Simplifies your end device development because you can actually manage your applications in a very scalable way. We don't reinvent the wheel. We just simply reuse what's already been here from a long time ago. With suitable compression, actually, we can bring IP, UDP, and co-op and get them to 2-3 bytes. I would really love to see them compressed to 1 byte, or even my wet dream 0 bytes. But this is a thing that we should really get to work here, and security is part of it. How do we do security when we have so much compression? And of course, bringing a new technology with this, if tomorrow you happen to define a new modulation or something like this, this thing already works. You only need to hire someone from the IETF for half a day to write your, or go to the NetConf doctors, and they will do this for you for free in one of their Sundays, and define your young module, and you can manage your whole network this way.
Yes, there's a question from Stuart Bryant from Jabber. It says, if it takes a day to authenticate, how does a service engineer do an install and replace and verify?
Sorry, can you repeat this?
So if it takes a day to authenticate, how does a service engineer do an install or replace and verify?
If it takes a server to authenticate one day, how does a service
engineer
yes,
do an install or replace and verify if it works?
Okay, so that's a good question. Actually, I've never thought about this, and this is when I say a day, it's a figurative speech. I think it will authenticate much faster. The point I wanted to make is that we are leaving the freedom to people that actually want to use this. We are giving this freedom to them. If they say, I really want certificate to authenticate my thing, and the certificates is 10 kilobytes or 5 kilobytes, and it will take over a lot of time. Well, it will work. Then it is up to the company that would like to do this to ensure that after 2 days or 3 days, to go there and update it. We allow using, and we say, okay, by default you should use pre-shared key or a SIM card, and it goes in 2-3 seconds. So that's okay, no problem for this. Then but that's a good point. That's a good point.
Juan Carlos Zúñiga, you mentioned that it's 19 bytes, and here you're also saying that it can run on top of LoRaWAN or Sigfox, which are some of them limited to 12 bytes. So are you assuming that you all absolutely needed compression to do this, or have you not tried?
You're talking about this one?
Yeah,
or?
for instance. Yeah, for instance, that could request 19 bytes.
Yeah, so this one is 19 bytes in which you reconfigure all these parameters in one go. So you could basically have a fragmentation on the IP layer with, or maybe use the CBOR block transfer, or just be aware. So your application can say, okay, I will configure on the first go the first half of the parameters, and on the second go the second half of the parameters.
This was application fragmentation.
Yeah. Yeah, exactly. The important part here is that we're not doing some kind of a nitty-gritty optimization that is for this specific use case. Here we are talking about technology that is operator grade. People are doing SDNs with Young. People are doing, you know, you have these huge network management servers and so forth, and we're just bringing this for free to all these technologies. So, thank you. So thank you very much. That's it. Use COSOL to manage your next LP1 network.
Okay. Well, thank you. Due to the previous discussions, we've eaten in quite a bit to the previously allocated half-hour discussion time. So we have more like 12 or 13 minutes. But I think if people, you know, keep their remarks reasonably brief and to the point, that would be useful. I don't know if Brian want to say anything.
Brian Haberman, yes. Since we do have a lack of time, what I'd really like to hear from people is, do they see a problem here? Do they see work that the IETF can do here?
So concentrate on whether there's a problem and whether it's a problem the IETF can help on.
Yeah, maybe I'll start, Srigandavelli. So I think I really like this area. I do not know if from this presentations today, I do not know if I identified very specific problems. That it was a general presentation, generally saying, I completely agree, I think. But my fundamental issue is like, I think we need to understand why these SDOs are not adopting IP. There is a cost aspect into this. If the cost that LoRa, for example, taking LoRa because that is of interest these days, if the target price range is like sub $1, can we have all of these stacks, you know, netconf yang, like, you know, IPv6, how does the device price change? I think fundamentally that is a problem, right? But I think if that is not a blocker, then I think pushing all of these and solving all the problems is absolutely, I think IETF should do that. You know, there are all of these SDOs doing those pointed things. They don't understand, not that we understand here, but there a lot of work already went in. Those guys don't understand that. At least if we can convince them that, you know, all these SDOs to adopt one standard architecture, it will help. It's in our interest. It's in community's interest. So in that sense, I support this work, but the problem statement is not clear. I think we need to identify precisely what are all the problems that we have to solve. That is important in my opinion.
This is Alex Petrescu. After following the presentation, I see three problems. One is a little bit IPv6 over foo. This is especially when we hear this variable MTU discussion, or when we hear that some LP1 do fragmentations, other LP1s don't do fragmentation. So this is typically questions for IPv6 over foo document. What's the MTU size? Who's doing the fragmentation? Maybe what is the form of the IPv6 address, and so on. So this is one topic that I see very well a potential work.
Sure.
Yeah, I don't need answers. I mean,
there are things to be said to answer this.
Yes, but if you are going to say that RPL is doing all this, then I don't want to hear. So okay. The second thing is this remote software update, okay, activity, over the air updates and so on. And this is a little bit of an application, right? It's not really IP. This is application over HTTP. Maybe co-op, if we agree, co-op is needed, but it's an application topic, remote software update. And the third, obviously, is the security. how do these devices get authenticated? Is it EAP? Is it PANA? Is it some link layers security that we don't need to touch, but others SDO will define? So these are the three things that I see. Thank you for listening.
Can I still say one word to answer this? Okay. I don't see LP1 as an IP over foo in the sense that we see 6LoW, for instance, being IP over foo. I see LP1 being more a group in like Hamnet or
Excuse me,
6
6LoW is not an IP over foo. 6LoW is 6LoW. Okay, when I mean IP over foo is an RFC that is called transmission of IPv6 packets over foo. That's IP over foo.
Maybe we could just go on to the next speaker.
Yeah, what I was just trying to say is we'll be looking at a global prime proposing more like an architecture than building blocks. Obviously, if we find that building blocks are missing, then we may go to an appropriate working group at the IETF if this exists, or if that's a small building block that can be done within LP1, then LP1 would be glad to do the work, I guess. But for instance, we saw fragmentation, and that fragmentation seems to belong to 6LoW. And if you take the example of 6-Dish, 6-Dish has been actually building this architecture, putting things together, putting demonstrators, and then asking 6LoW, RAW, and other working groups to provide some building blocks that were needed, right? So LP1 is considering the overall solution, is trying to make sure that whatever the IETF can provide to help this momentum continue and to be successful. That's basically what LP1 is about, building this solution, providing the help from the IETF to 1, 2, 3 selected organization, but not provide a particular component in that solution, not necessarily.
Okay.
So that's why the things that talked about best practice and a lot of things like
that. More people that talk.
Thanks. So Juan Carlos Zúñiga, I do see that there's work needed, and the problems, at least my takeaway is there's the solution that we have is not like one size fits all. This is a different animal, and we have to look at it on its own merits. And we were questioning the actual whole need of IP altogether. So it's not how we can make best IP for this, or another version of IP, but just not use IP, for instance. And I think it's worth giving it a thought. And I like the way you presented it from the vertical point of view, like not assessing just one layer and staying in our own little box, but understanding the whole system. I think it's important. Otherwise, we're going to create problems that will have to be fixed in a different group or in a different SEO. So I encourage the work to keep going. And to me, well, we still have to figure out a few things, but it seems like there's some good work that we can do in IETF to fix this.
Hi, Samita Chakrabarti. So first of all, I would like to thank all the LP1 team for such a great work on the analysis and the presentation. So the takeaway, I see that there are issues to solve, and I would like to say that there is already deployment on IP for constrained node devices in some of the SDOs. But I see the challenges you guys have on LPWAN is that you cannot just take one of the IETF defined RFCs or protocols such as 6LoWPAN onto your LPWAN because of the requirements of bits and bandwidth that you have on it. So I think that is there. I mean, we could solve that problem ideally. I think, you know, Carlos' presentation proposed it's an interesting idea for further dividing the fragmentation. And if we solve that, and I see that maybe some of the other management and aspects, so that may be discussed later, whether the rest of the COAP and management can fall in place. So I do see more work to be done on this case. And yeah, IETF should help solving or running IP onto those devices. Or I think the other one, is that they don't run IP really, but we need to have some proxy or gateway device to help them out. And that we don't want really, but that's the reality we have to accept. Thanks.
So Samita, in summary, do you see the need for this work to happen at the IETF? Do you think we can make it?
I said, yes, I think I see there is some work to be done at IETF, but exactly how and whether separate working group or distributing work on different working groups, that is probably, I don't know.
Suvitas again, thanks for some of the good presentations, but I think I have seen that initially there are a lot of different application use cases. I would say that since I am involved in some other external SDOs, there are certain applications still its deployment happening into an IPv6. There are some cases, there are reasons that why it was not run that way. I think that, of course, I'm not familiar with LoRa, but I heard in this Jabber that someone said for LoRa that they don't need any help, right? So those kind of statement is a little bit scary to me, because if other SDOs, external SDOs, they think that there is no additional optimization or additional work is needed, then who will be using this work, whatever we do it here? So from that perspective, I think it would be good to hear that what's the requirements from those SDOs and where there is a gap in IETF so that IETF can solve the problem. Otherwise, we can do this, then nobody will use it. Because in some cases, as I mentioned, that we are using IP stack and 6LoWPAN, IEEE, all these things, and it works. So it is getting deployed. So I think that it's a little bit premature to me hearing all these things that, okay, what exactly work that is needed to be done here.
So I want to cut off the line here, because I'm not sure we'll be able to get to these people. But
Go ahead, but I was just wanting, I mentioned, at least in my presentation, but I think Alex mentioned that as well. All this work depends on forming a relationship with 1, 2, or 3 SDOs. So by Berlin, which is where we would like to have the work group forming both, I think that one of the things that we have to prove is that we have established this relationship with 1, 2, or 3 SDOs, and that there is this common desire to build something together. And basically what we proposed here is our vision of the value proposition that we want to make to them. Now, if we go to a certain SDO and they say, not interested, okay, not interested, let's find another one. And there are a number of them which are really valuable. We mentioned Sigfox, we mentioned LoRa, we mentioned NB-IoT, and there are a number of good ones, lightweight, what's the name? Sorry, weightless. So there are a number of them. So if one is saying not interested, well, maybe our loss, maybe their loss, right?
Okay. Next.
Just to pitch in on this, so that's an interesting thing. Actually, I've been discussing with a lot of companies and several operators, and everybody is pretty interested in getting IP over these and getting the whole IETF stack over these technologies. And I think that our work here was to see, okay, can we actually do it today? Can we just simply use 6LoWPAN or something? And I get the impression that we have some work to do. And for me, the question was also, is there interest? Is there interest? And I get the impression, I mean, there is some interest, but we definitely need to work with the SDOs. We don't want to, go and force
Okay,
it.
if we're going to get the remaining people are going to have a chance to give a comment. I don't think we can really respond to them. Like people just to state that the line's been cut off. Just state whether you think, well, to the extent that you can, whether you think there's a problem, whether the IETF can help. And I don't think we can have any answers to the questions. We just want to get the comments of the remaining 4 people in line. Go ahead.
Okay. I have
Jabber.
2 comments from the Jabber.
Right.
The first one is from Stuart Bryant. Says the paradigm is very different from the one we are used to, and ironically much closer to the one when IPv4 was invented. And then from Patrick Kinney, I agree that using IP over these low throughput devices has issues and needs to be looked at.
Thank you.
Eric Nordmark. So it seems like if we're going to go, if there's some set of technologies that pushes the limits beyond what we have today, right? And I think fragmentation or sort of the MTU size is a key one. That's could be quite obvious. Then yeah, there is some work for the IETF to do here. Maybe there's other places where we need to do in the stack where we need to do additional optimizations. But I think the key thing is figuring out what is the whatever 1, 2, 3 technologies to go after here, and then focus on those and get those people to participate. Right? Once we get to that point, I'm not sure that it necessarily needs to be its own working group. Right? If these technologies are just things that naturally fall into existing ones, or whatever additional things we need to do fall in existing groups, that might be fine. Right? I think we can worry about that later. But the sort of next step is figuring out who can we engage here that's interested, that's where we can do something useful.
Thank you.
Suresh Krishnan. So I have like kind of mixed feelings. Okay, so the stuff that scares me most is like the list of technologies out there with like wide range of characteristics. So I see like 2 tracks we can take here. One of them is to find like some kind of common thread between the technologies and see what like we can do with the IETF, like some kind of guidance for them. Or the other way I see is like to make it more manageable is to pick like 1 or 2 of them and try to do like close alliances with them and then try to tailor these things. And it's not clear to me like what is it like track you want to take. Like I think that's something you probably need to nail down a bit, because we don't want to boil the ocean, because even though it's like interesting space, like so I don't know if you know, but I'll be taking over from Brian this week, and so we don't want to charter a group that's going to like take 20 years and like just keep doing stuff. Okay, so I think if you can scope it down to what? No, okay, you're going to say DHC. No, I won't. But the idea is like if you can narrow down the scope of work you need to do, I think there is good work to be done here, and a lot of it could just be like deployment guidance, like putting together a toolkit of IETF technology is already useful. Okay, so I really see value here, but I think if we're not ready at this point to like do something with this, right? Like maybe there's like some more thinking required from the proponents.
I think, yeah, I agree. There's interesting stuff for the IETF to do here, but I don't think that's the important question for this particular technology. We have a very specific business case that goes with it, and in these cases, we need something more than the IETF being interested in it. So we need a body that takes care about certification, very close, direct relationship with people who are actually going to be deploying this. They're going to have to pay rights of way, antennas, all this stuff, right? All the deployment costs. So this is something that would require not just IETF interest. I'm sure we have that. Most important thing here is whether to make it actually real and deployable is people actually from that community coming here. And I would have loved to see that presentations here from deployers, from the 3GPs of the world, LoRa's, Sigfogs of the world, from those guys. That's what I would like to see for as evidence that yes, they're waiting for us and they want us there, and that they would come here and do part of the work, and we'll go there and do part of the work. I think that's what's missing in my mind.
Okay, is there any objection to 2 more people? The one that's just Jabber speaking? Seeing no objection, okay, these are really the last 2. Go ahead. I cut off the line earlier, but go ahead.
Sorry. Carsten Bormann, I just wanted to point out some of these things look like they can become work items for a working group very soon. Some don't. But then we have IRTF, which can look at some of these issues. And in particular, we have a new research group called Think to Think Research Group, which might take up some of the more speculative points that were raised today. So if you think some things aren't quite ready for a working group yet, maybe you want to carry it to the Think to Think Research Group, and we might be interested.
Thank you. Last comment.
Thank you. Stuart Bryan says, with regard to whether this needs a new working group or it is added to the existing working group charters, depends on what critical mass is needed and what coordination is required.
Okay, so that's it. Thanks everybody for coming here. You should comment on the mailing list. There's a mailing list for this. And you can make your opinions known there and discuss the issues. Where are the blue sheets? There's one. Anybody who didn't sign the blue sheet should find one and sign it. And if people could bring them up to the front, I'd appreciate that. And so thank you all for coming. I think it was a good buff.